Cool. Okay. Thanks all for the invite. Very happy to be speaking to you today. Sorry I couldn't be there in person, um, but let's see how well we can do over Zoom. So, yes, as was just introduced, my name's Saga. I'm a researcher at Mistral, and I work on multimodal language models. But in a past life, I was a pure computer vision researcher working on representation learning, and that's what I wanted to talk to you about today. So, particularly, the title of my talk is Learning Visual Representations for an Open World, which has a few different components to it, but the central topic is representation learning. So, what is this? There's many different definitions, but to me, it's simply the task of taking an input and learning a function which keeps what we care about in it while discarding everything else. And in practice, in the modern day, this function is going to be a neural network, and it's going to give to us a feature vector on top of which we can do all of the interesting tasks which we know and love. So, for instance, if we want to do classification, the name of the game is first you train a feature extractor, you first train this representation, and then on top of that, you can train a linear classifier to say, okay, is this image a cat or a dog or a bird? Similarly, if you want to do object detection, you first train the feature extractor, and then on top of that, you can train a detection head to say, okay, exactly where in the image is my object. And finally, even in the world of VLMs or LLMs, these huge multimodal models nowadays, still there is at the core this feature extractor, which takes our image, represents it in some way, and passes this representation to our language model, such that we can do reasoning, open-ended chat, et cetera, et cetera. The other part of the title was open world learning. So what is this? Again, there are many different definitions, but in practice, it just means when the test distribution, the set of things on which a model is evaluated, comes from an unconstrained set of objects, categories, attributes, etc., which is slightly different to the setting which many of us tackle in academia. And in practice, most of the field has been addressing this by just training on ever and ever larger training sets, thereby making more and more problems closed world, i.e. that the set of things which we encounter at test time are the same set of things which we've encountered during training. So to illustrate this, on the left, I've shown ImageNet. So back in 2012, when AlexNet came out, ImageNet was by far the biggest image classification dataset, and it was seen as the largest scale at which we could train these models. Then Dino V2 a couple of years ago was trained on LVD 142 million, so 100x increase in the size of the data set. And now the largest image text data sets like Lion 5B are billions of images in size. So as I said, most of the community is tackling this problem of open world learning, where you want to encounter a broad set of object categories and attributes, etc. at test time by just training on larger and larger data sets. And what I wanted to discuss today was this problem of generalized category discovery, which we introduced a few years ago at CVPR, which tries to bake in these ideas of open world into the training algorithm itself to try and learn models or learn representations, which by default generalize better to the open world. So generalized category discovery at its core is an image recognition problem. I want to discuss before we get into the method exactly what is the problem we're trying to solve. It's an image recognition problem which, according to Wikipedia, is classifying a set of detected images into different categories. So if we look at these images here, this collection, I hope that everyone in the room can intuitively categorize these into these four clusters. So we know that the cats belong together, the birds belong together, the dogs belong together, and the squirrels belong together. And this is what we want our models to be able to do. And in practice, deep models can do this well, but as I said, in the closed world setting, when we have supervision for all of the categories, which we're going to see at test time. And if you look at the classic image classification problem, that's exactly what this is. We have a training set from a finite set of categories. This training set here is with blue boxes. We've got the cats and dogs, and we evaluate our models by simply evaluating them on new instances from the same categories, i.e. these unlabeled images of, again, cats and dogs. Now, the community has tried to expand this, relax the assumptions that we're making here by saying that, okay, now at test time, what if we don't only see cats and dogs, but we also see things from new object categories? What can we do then? And this is the problem of open set recognition. But open set recognition simply tries to say, okay, all the objects which we've not seen explicitly in our training set, what we're going to do is we're going to just put them all together in this K+1 bucket and say that these are new categories. So we're just trying to cluster all new categories together in their own bucket. Now, if you go really deep into the image recognition literature, you might have also come across a novel category discovery task, which I'll briefly outline. This is sort of the flip side of open set recognition, but now you've got a set of labeled images, which come from a set of known categories, and a bunch of images, which somebody has told you a priori with ground truth come from a different set of categories. And now you want to cluster them into related concepts, put all the birds and put all the squirrels together. And so the problem that I wanted to discuss today was a generalized category discovery, which is simply a way of trying to unify these two problems to make a slightly broader setting. But here we now say you've got this set of images. You've got this set of images. They could be labeled. It could be, some of which are labeled and some of which are unlabeled. And the unlabeled images, they may or may not come from the seen categories or the labeled categories. And now we simply want to cluster all of these unlabeled images together into their own semantic concepts. So this slide is just saying the same thing again, but in words. So given a data set, some of which is labeled, generalized category discovery is a problem of assigning a category to all of the unlabeled instances. Now, something that I want to clarify here is that we're expanding the setting by saying that, okay, in practice, when you've got a model, when you've got a set of images like this, there's no reason to explicitly have this crane test held out split. And you can, if you can in practice crane on all the images together, so long as you don't make the assumption that you have labels for every single category. So how do we go about solving it? Well, if we were doing a standard image recognition approach, we would train a feature extractor and a linear classifier, and we would train end-to-end with ground truth labels. Now, this paradigm that I'm describing here describes almost every image recognition model, all the way from AlexNet back in 2012, all the way to Dino v3 from this year. There is some feature extractor which can be trained however, but when you want to do the classification task, when you want to do the recognition task, you have to train it end-to-end with ground truth labels. Now, in novel category discovery, which, as I said, is a subset of the problem we're trying to solve, where we've got a set of images which we know come from new classes, all papers had a similar idea, which was trying to train exactly the same kind of model, but now instead of ground truth labels, using pseudo labels to train the linear classifier. And the name of the game here was to find new and inventive ways of mining these pseudo labels automatically from this unlabeled data. So when we tried to apply the same setting to our generalized category discovery setting, where in practice we have both old and new classes in the same set of pools, and we want a single model which can perform well on both, we found that training the same linear classifier on both ground truth labels and pseudo labels actually significantly degraded the performance of the model and ended up overfitting this linear classifier to the ground truth labels, which have clean supervision. So in practice, what we did is we got rid of this linear classifier and we said, okay, what if we can just learn a feature representation which out of the box can generalize to new categories and do away with this linear classifier and do classification directly in our feature space. More precisely, what we did is we started from a self-supervised model. So this is a model trained without any supervision whatsoever. There's no categories involved here at all. And in particular, we used the Dino model. Back in the day when we published this work, there was only Dino v1, but Dino v2 and Dino v3 are drop-in representations in the method I'll describe today. And these models are very interesting for many reasons, but particularly to us, they had two interesting features. The first is these self-supervised vision transformers turn out to be very good nearest neighbor classifiers. And as I said, we want to do classification directly in the feature space with something like nearest neighbor. And so we thought that a model which was good at this out of the box would be good. And secondly, we found that the Dino models attend to semantic object parts. And while we do want to be able to generalize to new categories, we hope that object parts might generalize between the train set, between the label set, the label categories and the new ones we want to discover. And I'll give you some examples of this in a moment. So once we've got this Dino backbone, as I mentioned, we've got some labels for a finite set of categories, and then we've got this big unlabeled set which could contain the same categories or new ones. I want to learn a representation on all of this data. So what we do is we do a contrastive learning algorithm using both the supervised and self-supervised objectives. So on the labels which we have, we use a supervised contrastive loss, pulling together different images from the same object category together and pushing away images from different object categories. And at the same time, we have a self-supervised loss applying on all the data. And here we pull together different instances. We we push apart different images which come from different instances. So simply two different images are treated as dissimilar. Meanwhile, two augmentations of the same image are treated as similar, and we pull those close together. So here you can see that the objective, which we're running on all of our data on the unlabeled set, is very similar to the objective which we're running on our labeled data. And here we hope to use the labels to only nudge the representation in the right direction and avoid this overfitting problem on this clean set of labels which we have for the labeled set. And then, as I said, we want to be able to do classification directly in the feature space of the models. We don't want to train a linear classifier. So we do k-means clustering to simply group all of the all images from a related concept in the same bucket. So k-means, I'm assuming that most people might be familiar with. We made one small adjustment to it to account for the fact that we did have access to some labels, where in the cluster assignment step, we made sure that all images from the same label category were assigned to the same cluster. Okay, so that's the method. Discussing a little bit the results. Well, the boring results are when you, in any paper, the numbers for the method you're showing have to be higher than the numbers for the methods before. So indeed, we found that our method was a little bit better than these linear classification methods. What was particularly interesting to us is on fine-grained data sets, shown here as herbarium 19 and CUB. The gains were particularly stark compared to previous methods. And these fine-grained data sets are ones where there's where all object categories are very similar. There's very small differences between different object categories, making the classification problem much more challenging. The other thing which we found very interesting was actually the way in which we thought the model generalized between these old and new categories, in which it really generalized to the open world. So these transformer models, whether it's a LLM or whether it's a dyno model, they do self-attention between an input within an input sequence. So here our input sequence is a sequence of patches where the patches together represent the image. And the attention mechanism is done independently with different heads, such that different heads can attend differently to the image in the same way, in independent ways. And what we found is that different heads in our method attended to different object parts. So if you look here, I don't know if you can see my cursor, but if you look here in the panel on the right, labeled Dyno VIT after fine-tuning, on the top, we can see that we have one head which explicitly learns to attend to the windshield of the car. We have a different head which explicitly learns to attend to the headlight of the car, and finally a different head which attends to this wheelhouse. Similarly, if you look at the birds at the bottom, we can see that we've got one head which attends to the beak. We've got another head which attends to the eyes, and another head which attends to the belly. Now, the thing that we find interesting about this is that, like I said, we are trying to discover new categories, new clusters in our unlabeled data. But ultimately, we think there is something which must generalize from the old to new categories. And we thought that object parts, so birds, eyes, beaks, are these underlying concepts, this underlying structural problem which can generalize between old and new categories. And we think that a representation which explicitly encodes this has a better chance of being able to do so. So in the final couple of minutes, I wanted to discuss a little bit about why we care about this problem at all. Some pushback I've had about this setting is that it's still operating this traditional image recognition, classic machine learning paradigm from the sort of late 2010s, early 2020s, where we have a finite training set, we've got a finite test set, everything falls into discrete category. And people say, well, in practice, now we've got these very large scale data sets which have both image and text. Why is it that we still care about this kind of finite discrete category problem? Well, my first answer to this is that in practice, this still remains a very relevant task, particularly in cases of fine-grained recognition, where we need a lot of expert knowledge to be able to classify things into a given ontology. So a data set which we hill climbed on was CUB birds. And here you can see pairs of different categories within CUB birds. They're very, very visually similar, and in fact, semantically also very similar, and requires real expert knowledge often to discriminate between these two. And the aim of methods like this is the hope of methods like this is to be able to do this kind of organization, this kind of ontology mapping automatically. Another example which we tackled and which we hill climbed on was herbarium. So this is an even broader data set. So CUB is only 200 classes, again, very fine-grained. herbarium, which is a data set which some of you might have come across if you work in this space, actually has 1 million images which come from 15,000 categories. And here you can see that the knowledge is even more specialized. Without very hard-won expert knowledge, it's very difficult to be able to distinguish between two images from in different object categories or the same object class. And mapping out this ontology is a very expensive process which burdens a very small set of experts. And again, we hope that this sort of category discovery method will allow us to learn a representation of the data we have, and then expand this representation out to the long tail and hopefully automatically discover us new knowledge. And the final thing I would say is that nowadays I do indeed work on settings where we don't have necessarily finite categories like this, but instead we work with very large models which have billions of parameters trained on billions of images, etc. And in that kind of setting, the data is inherently image text. It does not fall into these discrete buckets. However, in practice, the problems that we encounter are exactly the same, which is to say that we have a representation in this image here. This is a figure from our Mistral paper, our VLM last year. Still in these VLMs, at the core of it, as I said, is this vision transform with this visual representation, which then allows the VLM to reason broadly over the image. And it still remains a fundamental bottleneck, which is that no matter how big your training set is, the real world always has novel concepts. It always has things which haven't been well covered in your training distribution. And it remains very important to be able to train representations which generalize beyond the things which you've explicitly given the model in the training set. So that's kind of all I had today. I think that's my final slide. I think we've got 5 minutes for Q&A, if I'm right, Nico. Happy to take any questions if there are any. Thank you.